So we left off on Monday talking about this concept of total internal reflection. And we said the total internal reflection is that reflection of a wave, specifically in this case, we're talking about electromagnetic radiation or even visible light, off of the boundary between two surfaces. As opposed to refraction, this reflection takes place when we exceed this minimum angle that we call the critical angle. Now, there was one thing that was absolutely required for this to happen. When we're going from one medium to the other, total internal reflection can only happen going one way. If we have a low index of refraction up here and a high index of refraction down here, and we've got that ray of light coming down this way, strikes the boundary, where's it going to refract? Toward the normal line or away from the normal line? Does it speed up or slow down? If it slows down, it's going to bend which way? It's going to bend toward the normal line. Total internal reflection can never happen when light goes this way from a low index of refraction to a high index of refraction. It can only happen when we go the other way from low to high index of refraction. Well, why? Why is that the case? Why can it happen when we go from a high to low index of refraction? If the ray of light strikes the boundary, it's going to refract away from the normal line because it's going to speed up. There's still no reflection taking place here, but at least we're bending away from the normal, which is the basic requirement in order for total internal reflection to take place. If we increase the angle of incidence a little bit further to something like this, well, then the angle of refraction is going to be more. In fact, it may be enough to actually cause the light to skip right along the boundary between the two surfaces. If we increase the angle of incidence even more, then what we're going to find is that refraction doesn't take place. It doesn't skip along the boundary, rather it reflects right off of the boundary. And then we've got the law of reflection kicking in, such that the angle of incidence equals the angle of reflection. This angle right here, this blue angle, theta I for the blue ray there, is what we call the critical angle. It is the minimum angle at which total internal reflection begins to occur. Anything above that angle, reflection occurs. Anything below that angle, refraction occurs. Does that make sense? We showed you this picture here on Monday. We had a fish in the bottom of the pond. And we're trying to look at that fish. Okay, so you got a guy standing on the side of the pond looking at that fish right here. There's lots of rays of light reflecting off of this fish. It's coming from the sun, coming from a light bulb up there, whatever, probably the sun in this case, unless it's a fish tank. Okay. The rays of light reflect in all different directions. You got rays of light coming up here, coming there, whatever, and they're all refracting in different directions when they leave that water-air boundary. But there's one ray of light that reflects off of that fish and refracts right into the eyes of the observer there. That observer now sees the fish because the ray of light coming from that fish is refracted into that observer's eyes. But that observer doesn't see the fish where the fish really is. The observer thinks, or at least the brain of the observer is tricked into thinking, that that ray of light always traveled in a straight line. So he's going to think that the ray of light came from over here. That means that according to the observer, the fish isn't deep and right there. Rather, the fish is shallower and right here. You're trying to catch that fish, you're going to put your fishing line in the wrong place because you think the fish is right here as opposed to right here. This has nothing to do with total internal reflection yet. It's just refraction. But what happens if I move this guy back? This guy gets moved back here. Well, this ray of light that did enter this guy's eyes now sails right above his head. If there was still somebody there, that person would still see. Let's put somebody there, actually. If there was still somebody there, that person would still see the fish in that different position. But the second guy, the guy that's in behind him here, doesn't see that fish there anymore because that ray of light that refracted off of or reflected off of the fish and then refracted from the water-air boundary doesn't strike him, doesn't hit his eyes. We need another ray of light to refract into his eyes. Maybe it's this ray of light. Okay, this ray of light comes from the fish, but this ray of light, you notice, strikes the boundary at a bigger angle, a bigger angle of incidence than the blue one did. If that red ray is striking the boundary at a bigger angle than the critical angle, what's going to happen to that red ray? It's going to reflect, right? If it's striking it at a smaller angle, maybe it goes up here. The guy observes it. He's going to observe the fish in a different place, but he's still going to observe the fish. If that red ray strikes it at a bigger angle than the critical angle, then the red ray will reflect. And what does this guy over here see? Sees the top of the water, right? Doesn't see any fish because he can't see down in the water because all of these rays are reflecting off of the water-air boundary. Does that make sense? I've never gone diving, like scuba diving. But apparently, and this makes sense to me, using physics concepts, it makes perfect sense to me. Apparently, if you go scuba diving and you go deep enough and you look up, you can't see out. Is that right? You've gone scuba diving before, right? You can't see out. What do you see? Nothing, really? Okay, in the end, the rays of light that are coming from the bottom of the pond are going up, and at certain angles, other than directly right above you, they're exceeding the critical angle, so those rays of light are reflecting off at the boundary. So basically what you're seeing at that water-air boundary is not what's outside, but what you're seeing is reflections of what's inside. So if you're, I assume if you're deep in a swimming pool, who lifeguards there? Are you guys lifeguard? You guys ever notice that? I think when you lifeguard, you have to do that thing where you go down to the bottom of the deep pool and pick up a certain weight and bring it up. You guys notice when you're at the bottom of the deep pool, if you look up, that you can't see out? Yes? I don't know. I've never really noticed that because when I go to the bottom of the deep pool, my ears hurt so much that I just get up to the top of the pool really, really quick. So I've never really observed this, but again, it makes sense physics-wise that you're not going to see out of the pond or out of the pool because you're going to have all this total internal reflection taking place off of the boundary between the water and the air. A total internal reflection. Another example of total internal reflection. Here's a diamond. Everybody knows what this, this is the standard cross-section of a diamond, right? Forget about the numbers in there, 60 to 61%, 98.5 degrees. I don't care exactly about the angles and the percents, and it doesn't even matter to me right now. The basic shape of it, everybody's familiar with, right? You can see a diamond from the top that's square or oval or circular or whatever. But from the side, they all look the same. They're all cut this way, or at least they better be cut this way. If they're not cut this way, then they're not worth very much. When I bought a diamond for who's the person who's now my wife, a number of years ago, I went to this store called Spence Diamonds. You guys have probably heard the commercial on TV with that really annoying guy. I'm pretty sure that was actually the guy that sold me the diamond. I'm pretty sure it was because it sounded exactly like him. So I'm pretty sure it was the same guy. Anyways. I'm looking around, and he shows me these things, and he takes me into his office and explains some things. And he says, at Spence Diamonds, we like to explain, what makes a good diamond. So he's explaining that there's 4 things that are associated with a good diamond and, a valuable diamond. The 4 C's, they call them. In no particular order, the clarity of it. So you want a clear diamond. You don't want a diamond that's foggy, right? Because some diamonds are foggier than others, and they're not as valuable. The clearer it is, the better it is. The carats, the size, right? The size of the diamond obviously matters. The bigger the diamond is, the more expensive it is, and the more valuable it is. The color. Most diamonds have no color. If it has a little bit of a yellowish tinge or something, then that's not very good. Nobody wants a little bit of a yellowish tinge. He said if it's really yellow, then sometimes it can actually be worth more because it's different, right? But nobody wants a little bit of yellow because it just kind of looks bad. And the final one was cut. He said the cut, believe it or not, is just as important as any of those natural things like clarity or color. The cut has to be perfect. If the cut's not perfect, then the diamond doesn't sparkle very much. And he went on to explain why. Okay? And after he explained why, by the way, he asked me a little bit later on, he says, so what do you do for a living anyways? I told him what I did for a living, and then he said, kind of look on his face was kind of like, oh. He says, did I pass? He did. He did a perfect job of explaining what I'm about to explain to you right now, basically. When a ray of light enters this diamond, most rays of light that enter this diamond are going to enter from above. So let's look at a ray of light that's entering this diamond from above. Goes straight down. Okay, when it goes straight down, it's going to go through that top face straight in. It's going to slow down, and it's going to slow down quite dramatically. But it's not going to change direction because for the most part it's going in a straight line already. It keeps going in a straight line. It hits this boundary right here between the diamond and the air. What's going to happen to it? Well, you would think that that ray of light that's coming into the diamond there and then about to leave the diamond would leave the diamond, and it would speed up so it would refract away from the normal line. But if the diamond is cut properly, then this angle right here that it strikes the boundary at, the angle of incidence, will exceed the critical angle if it's cut properly, if it's cut at the right angle. If it exceeds the critical angle, then what's going to happen to that ray of light? It's going to reflect instead of refract. So it reflects over here. Well, now it strikes this boundary. If it exceeds the critical angle again, then it's going to reflect. If it doesn't exceed the critical angle, then it's going to refract. Well, we want it to exceed the critical angle. If this diamond is cut properly, then it will exceed the critical angle, and it's going to reflect again, and it's going to come back out here. The sparkle that you see in a diamond is because of reflections. If a ray of light comes straight through here and refracts out this way, there's no sparkle. If a ray of light comes down here and reflects, goes this way, then there's a sparkle. Now, if it's cut kind of okay, but not perfect, then the ray of light coming down here might reflect off of this one, but not reflect off of this one. So it'll sparkle, but it's not going to sparkle as much as if you get a couple of reflections from each ray of light. Why does diamond do that more than other materials? Because diamond has a higher index of refraction than other materials. Because it has such a high index of refraction, the critical angle for diamonds is quite a bit lower than it is for other materials. If the critical angle is lower, it makes it easier to exceed the critical angle, right? You got another material, maybe it's cubic zirconium, which also has a high index of refraction. It's about 1.9 or 2 as a critical angle. Well, what you might find is that the first ray will reflect, although the angles involved would have to be different, right? You'd have to have this cut differently. The first one might reflect and you get a sparkle, but the second one wouldn't strike at the right angle to cause reflection, and therefore it would refract. So you get one sparkle instead of 2. It's good, but it's not as good of as a diamond. Okay? So it's valuable, but it's not as valuable as a diamond. Ladies, when some guy gives you a diamond, eventually, it should be a long time from now, because if it happens anytime in the next few years, turn them down. Okay? Guys are bad right now. They stay away from guys right now. At this age, they're all bad, every single one of them. They're just trouble. But when that happens, someday when that happens, look at the diamond, look and see if it sparkles. Okay? And if it doesn't sparkle, say to the guy who loves you deeply and is giving you this diamond ring, say, you know, you might want to take this back. I don't think it's cut properly. The light coming into this diamond isn't exceeding the critical angle, and therefore there's no total internal reflection taking place, and therefore the diamond isn't sparkling. I love you dearly, but I want total internal reflection. Guys, when you go to buy that diamond, if the person's selling you the diamond, if you buy that diamond and it's not sparkling, then say to the person that's selling you the diamond, listen, I like it. It's a nice ring. I'd like a little more total internal reflection. Can you help me out with the total internal reflection thing? Okay? And if they don't, then move on to the next one. Girls, hey, if the guy won't do that, move on to the next one too. Okay, move on to the next door as well. Total internal reflection occurs in water. It occurs in diamonds, and that's why diamonds sparkle. It also occurs in something that we call an optical fiber or fiber optics. You guys have heard of fiber optics, right? Fiber optics or an optical fiber is a wire, basically, that carries information not via electrical impulses like regular conducting wire, like regular copper wire does, but rather information is encoded in light. That light carries the information very efficiently from one place to the other. There's very little signal loss, a lot less signal loss than there is in an electrical cable. How does that work? Well, here's your optical fiber, which is basically glass. Okay, an optical fiber is basically glass. It's a kind of a flexible glass. This ray of light that is carrying the information coming up here, it strikes the boundary between the glass and the air. Well, if that ray of light exceeds the critical angle, which it probably does right there in this diagram at least, then what's going to happen to it? It's going to reflect. Well, then it's going to reflect down and it's going to hit the other side. If it exceeds the critical angle, then it's going to reflect again. So you get this ray of light that is constantly, nonstop, reflecting off of the boundary between the glass and the air with no signal loss. So it keeps going. Now, when could you get a signal loss here? When would some of this light escape? If there's a break in it, sure. Then it's all going to escape, right, if there's a break in it. Yeah, you got to be careful with fiber optics to not bend the cable too much, because if you bend the cable too much, what's going to happen? What happens if we go and do this? Well, now the angle of incidence is quite a bit less. Now what happens to it? Well, it might still reflect, depending upon how much it's bent, or it might leave, speed up and bend away from the normal line, but still leave. And no total internal reflection, meaning you get signal loss. Make sense? All right. How are we going to find this critical angle right here? The angle at which total internal reflection occurs in this fiber optic cable. How are we going to find the critical angle between diamond and air so that we know what angle we have to cut the diamond at? How are we going to find the critical angle right here so that we know at what point we have to stand in order to see the fish? It's not as hard as you might think. Let's draw a picture of total internal reflection happening again. The same diagram as we've drawn a number of times already. We've got a high index of refraction right here, and we've got a low index of refraction right here. Because remember, if we're going from low to high, it doesn't work. Going from high to low doesn't always happen, but it could. The point at which total internal reflection begins to occur is the point at which that ray of light skips along the boundary between the two materials. We're going to label that theta I, that angle of incidence, theta C, the critical angle. What is the angle of refraction right now when total internal reflection begins to occur? What's this angle of refraction right here as this light ray skips along the boundary? What is it? No, not 0. Not 180. Somebody said it. 90. It's always measured from the normal line. So theta 2, or the angle of refraction, would be 90 degrees. What we want to do when we're solving for the critical angle is use Snell's law, sine theta 1 over sine theta 2 equals n2 over n1. But we're going to replace the whole theta 1 with theta c, and we're going to replace theta 2 every single time with 90 degrees. If it refracts at 90 degrees, in other words, if it skips along the boundary between the two materials, then that means we're at the critical angle. Well, let's set the angle of refraction equal to 90 then and find the critical angle. By the way, what is sine 90? 1. So we can actually just drop that entire denominator, right, if we want to. Sine theta c is equal to n2 over n1. Or theta c is equal to the inverse sine of n2 over n1. The reason I showed you where that equation comes from, sine theta c over sine 90 equals n2 over n1, is because this doesn't appear on your data sheet. Snell's law does, but you've got to come up with the equation for theta c, the critical angle, yourself. I've seen this asked on a test several times. Find the critical angle for this. Okay, it's usually, a page of information, and you got to sift through and figure out what's important. But in the end, the question is, here's two indices of refraction. What's the critical angle? These all should be fairly simple because you're only given two things, right? N2 and N1. What's going to happen if you mix them up and go N1 over N2? You're going to get an error on your calculator. It's going to show up as an error. So it's almost foolproof. If you remember that it's n something over n something and you mix them up, your calculator will tell you. Okay, fix it, switch it around, go the other way around. Let's try this example, 13.5 on 673. What's the critical angle for the quartz glass air interface? Well, we need some indices of refraction. The index of refraction of air is 1.00. The index of refraction of quartz glass, if we go way back here, quartz glass was 1.47. We want to find theta c. Tell me which one is theta 1, which one is n1 and which one is n2. N1 is what? N1 is the quartz glass. How do you know that? Good. It has to go from a high index of refraction to a low index of refraction. Having said that, if you got mixed up with it, you'd still get away with it because you'd do the question, you'd get an error, and you'd know to try it again. Let's say from scratch here, sine theta c over sine 90, because we're always setting theta 2 equal to 90 degrees in these questions, is equal to n2 over n1. Or we're going to say sine theta c is now equal to 1.00 over 1.47, or theta c will be equal to the inverse sine of 1.00 over 1.47. What do we get for that theta c? What is it? 43? We're going to round that to 3 digits, 42.8, 42.9 degrees, okay? 42.9 degrees. Anything above 42.9, what happens? Sorry? Reflection. Anything below 42.9, what happens? Refraction. It's not that hard, is it? Like I say, it's almost foolproof. If you know the indices of refraction and you mess up on it, your calculator is going to tell you messed up on it. So fix it. Try not to mess up, but it's twice as much work then, but at least you can fix it. All right, let's take a look at the problems that go along with that. Question 1, A, B, and C on 673. And we'll take a look at that in a minute if we need to. All right, guys, if we have no issues with this, then we'll move on. We're going to move on beyond just general refraction now, and we're going to talk about lenses, curved lenses, specifically, just like we talked about last week, curved mirrors. There's two types of curved lenses, just like there were two types of curved mirrors. We've got converging and diverging, but look really close at what I've got written down here already. Converging is convex. Diverging is concave. For a mirror, it was the exact opposite. For mirrors, if we had a converging mirror, it was a concave mirror. A diverging mirror was a convex mirror. With lenses, it's the exact opposite. Converging is convex, and diverging is concave. It's probably a good idea if we start talking about these in the context of converging and diverging and not in terms of convex and concave. Because when we talk about converging and diverging, there's no mistaking focal points, are they positive or negative, and so on. If we start talking about convex and concave, then there's a good chance we're going to get mixed up between lenses and mirrors and start messing up on those sign conventions, positives and negatives, and so on. So converging lens is a lens, just like a converging mirror was, a lens in which all of the rays parallel to the principal axis will converge at the focal point. And a diverging lens is a lens in which all the rays parallel to the principal axis diverge away from the focal point, just like we had with mirrors. Now, what I want to do with you right now is show you all of the rays parallel to the principal axis in a converging lens, okay, a converging or a convex lens. I'm going to take out of the box here a convex lens or a converging lens. It's like a magnifying glass, right? This is exactly the opposite of what most people, at least most younger people, and I would include with that for the purposes of this argument myself, even though I'm not so young anymore. Most young people that need glasses need diverging lenses. Okay? As we get older and the muscles in our eyes weaken a little bit, then we tend to need converging lenses to correct farsightedness. A lot of people end up needing both, right? So you end up needing bifocals. The top of your lens is converging, and the bottom of your lens is diverging, or the other way around. I forget which one it is. Okay, this is a converging lens. This is the one that I will probably need someday on the bottom part of my glasses so that I can read the newspaper. Not quite there yet. The eye doctor last time asked me, any problems? And I said, well, the one problem that I had that I've never had before was just a couple of weeks before my eye appointment. My son got a splinter in his finger. So he wanted it out, desperately wanted it out. So I took a needle to take the splinter out of his finger. And for the first time in my entire life, this happened about 2 months ago, first time in my entire life, I'm going to do this with a needle in his finger, and this is what I do. And I could see better when I took my glasses off than before I took my glasses off. The eye doctor kind of just laughed and said, it's starting, basically. He said it'll be a while before I need bifocals, but it's starting. All right, so we have this converging lens here. It's mounted to this meter stick now, and we're going to mount a card, which is going to be our screen. We're going to call it our screen. Also going to mount to this meter stick. Right now, this card is going to be mounted at a random spot on this meter stick. So we're not going to see anything in this card. We're not going to see any kind of image at all on this card. It's just there. Okay, if we put this card in a very specific spot, though, and aim this meter stick or this convex or converging mirror lens, whatever it is, it's a lens, right? Yes. Converging lens at a far-off object so that most of the rays are parallel to the principal axis, then what we should see is a real image formed at the focal point of this lens. So what I got to do is aim this at a far-off object. We'll pick the condos across the street probably, because they're far enough away. Rays are coming off it at all different directions, but the rays that make it as far as this lens and go through the lens have got to be pretty much parallel to each other. If we adjust this card back and forth and we see a real sharp focused image of those condos from across the street on that card, then we found the focal point. We know what the focal point of this lens is because we know the rays parallel to the principal axis should converge at the focal point. I need someone to flip the lights off over there, please. And if you can grab that blind, actually, let's do this one. That allows less light in there. Brittany, can you grab that blind? Maybe up. There we go. It's not a good bright day. It's too bad. It works better on a good bright day, but it should still work here. Right now, I'm aiming more or less at those condos. Right now, I see nothing on that card. If I move that card back and forth, then what I should see at one point is, right about here, some clouds and some upside-down condos on this card. You guys see that? Hey, come around to here, guys, if obviously people on the other side of the room can't see this. You see the clouds better and the blue sky better, but you could see a really small version of these condos, albeit upside down, but still, fairly clear image of those condos on this card. What do we call this, a real image or a virtual image? It's real because it's projected onto a screen, right? The focal length of this lens is going to be somewhere in the range of about 9.5 centimeters. We know that because the card and the lens are about 9.5 centimeters away from each other right now. We need to see, I'm off by a little bit there now. It's hard to see the road there. You see that? It's hard to see the road there. If we see the road, then we can actually observe cars driving upside down sometimes on this card. All right, so we've seen from the demonstration that rays parallel to the principal axis will converge at the focal point. There are other rays that are reflecting off of the object as well. Where do they go? Well, we've got rules, just like we had for mirrors. There's a million rays coming off of the object. We're going to pick two of them. First ray is going to be parallel to the principal axis. It's going to go through the focal point. Second ray, going to be somewhere else. It's, in fact, going to go from the top of the object through what we call the optical center. The optical center is this spot right here. We'll call it the OC. And it goes straight through. Where do these lines intersect? Well, that's where the image is that's formed, wherever these lines intersect. Let's draw our object way out here. By the way, what kind of lens is this? It's a converging lens. Let's not call it convex. Okay, let's call it converging, even though it is a convex lens. First ray is going to go parallel to the principal axis. It's going to converge down through the focal point. Second ray is going to go from the top of the object down through the optical center, and it's going to keep going through the optical center. Straight through. Looks like this. The image formed is going to be right here. What are the characteristics of that image? It is, number one, smaller. It's inverted, and it's, what is it? No, it's not virtual. It's real. Now, Brittany asked a question back when we did mirrors. She said, well, can't we just remember that if it's on the opposite side as the object, if the image is on the other side of the mirror as the object, then it's a virtual image. Yeah, that works with mirrors, but with lenses, it's the exact opposite. If it's on the opposite side, it's a real image. So Brittany, as I was saying back then, I suggest that you don't remember it that way because you're going to get mirrors and lenses mixed up that way. My suggestion would be to remember it as solid lines intersecting. It's a real image. Then the same rules apply for both mirrors and lenses. It is smaller, it is inverted, and it is real. Next one that we're going to draw, we've got an object this time at, by the way, this would be our focal point, and this would be, we're going to say 2F. We're not going to say center of curvature, because that's not necessarily the case, but it is twice the focal length. It corresponds to what the center of curvature would be for mirrors. Over here on the left-hand side, we've got spacers again. This would be F, this would be 2F, but it's not really the focal point because that's not really where rays converge. So again, it's just a spacer. If the object is at 2F, twice the focal length, what are the images going to look like here? First ray, top of the object, parallel to the principal axis, then it goes down through the focal point. Second ray goes down through the optical center, keeps going straight through. They converge right here. What can you see about this, the characteristics of this image? Larger, smaller, same size? Same size. Is it upright or inverted? It's inverted, it's upside down. Is it real or virtual? It's real. So we've got a situation here where we're projecting an image onto a screen, but the image is exactly the same size as the object was. So there's not going to be a whole lot of application for a situation like this, because generally speaking, you're not going to want to make something the same size as the actual object. Otherwise, it probably defeats the purpose of even doing it. of even trying to project it onto the screen. Let's try the next one now. Next one is when the object is in between F and 2F. Of course, we're going to draw the first ray from the top of the object parallel to the principal axis. It's going to go down through the focal point. Second one is going to go down through the center of curvature, or not the center of curvature, but the optical center, and it's going to go straight through. It's going to look something like this. They're going to intersect over here, giving us an image that is larger, it's inverted, and it's real. Where have you seen this before? You're seeing this right now, literally right now. The object inside that LCD projector that's hanging from the ceiling right now is really small. The image is really big. You're seeing a bigger, real image form. The only thing is, this image that you're looking at right now physically is right side up, right? Take a look at the projector. The projector is upside down. So the image formed is, it's an upright image, but if the object is inverted, then it makes sense that it should be an upright image, right? If the object is inverted. You see that in movie theaters as well. In movie theaters, we see this giant image. Well, we see this giant image because of the focal length of the lens is different, obviously, than movie theater. This giant image that's right side up. Well, the picture's upside down. The object is upside down. Still an inverted image relative to the object. Let's try the next one. This time we've got an object right at the focal point. First ray parallel to the principal axis. It's going to refract down through the focal point. Second one's going to go from the top of the object down through the optical center. Go straight through. Where do those guys intersect? They don't. So let's extend them back here. Where do they intersect? They don't. So what kind of image do we have here? There is no image. There's no characteristics of it because there is no image. Okay, next one. This time, we've got our final diagram for a converging lens where we have the object in between the lens itself and the focal point. First ray is going to go from the top of the object. It's going to go parallel to the principal axis. Then it's going to go down through the focal point. Second one is going to go from the top of the object down through the optical center. They don't converge on the right-hand side, so we're going to have to extend the refracted rays up here. They do converge up here somewhere. What are the characteristics of this image? It's larger. It's upright. And it's virtual. Where have you seen this before? You ever used a magnifying glass to make something bigger? Where do you have to hold that magnifying glass relative to the newspaper or whatever it is that you're trying to make bigger? Close to it, right? And when you look through that magnifying glass, what do you see? You see an upright, virtual, bigger image. Why do you have to hold it close to the object, close to the newspaper, whatever it is that you're trying to magnify? The object has got to be inside the focal length. So if you don't put the lens close to the object, then the object isn't going to be inside the focal length. Hey, we found that lens that I showed you the demonstration with, focal length was about 9.5 centimeters. Okay, if I put this lens and this little piece of paper on Elizabeth's page within 9.5 centimeters of each other, then we should have a magnifying glass. We should be able to see whatever she's written magnified. Larger, upright, and virtual. If we put it out here, there's a point when I see nothing. That would be at the focal point, right? But if I pull it out even more, then what happens? Things go all wonky, and things appear to be upside down. Right? Why do they appear to be upside down? Well, because I'm pulling the object outside of the focal length. Does that make sense? This is a perfect example of a movie theater projection screen. This is the perfect example of a magnifying glass, right? Which is basically the kind of lens you have in your eyeglasses if you need reading glasses. You got magnifying glasses, right? It's built-in magnifying glasses. I'm going to do one more ray diagram with you. What do you think it's going to look like? What kind of lens is this? This is a diverging lens. All rays parallel to the principal axis here do what? They diverge away from the focal point. This is F, this is 2F. Let's say we've got an object that is way out here in this diverging lens. First ray is going to go parallel to the principal axis. It's going to refract away from that focal point. Second ray is going to go from the top of the object right down through the optical center, just like it was in the last set. Those guys intersect anywhere? They don't. What do we got to do? To extend them back. Hey, there's converging, right? They come together right there. Intersecting lines. Is it real or virtual? We've got one solid and one dotted intersecting line. Is it real or virtual? We said if it was real, we'd have solid lines intersecting. We said if it was dotted, we'd have, if it was virtual, we'd have dotted lines intersecting. What do we say when we have one solid and one dotted? Here's the thing. We don't actually have a solid line and a dotted line intersecting here. We don't want a refracted ray intersecting with an incident ray. So what we're really got to do here is extend this blue line that you see here, the second blue line, back. Let's extend the refracted portion of it back. It just happens to refract back or to be extended back upon itself. Now what do we have? The extensions of the refracted rays are both dotted, and these two dotted rays intersect with each other. So we've got an image formed right here. That image is going to be smaller. It's going to be upright. And it's going to be what? Real or virtual? Virtual. So if you want to see this, you've got to physically look into the lens in order to see it, as opposed to trying to project it onto a screen. I'm sorry, say it again, Daxon. On the converging mirrors or lenses? Yeah. Okay. It's supposed to be the center there as well, Daxon. Yeah. Yeah. But having said that, Daxon, we're still fudging that a little bit when we do that. Daxon's question was a good one, and it leads to an even better question. If we go back to these lenses, say, well, these rays went right, let me just erase this so I can redraw it for you. We got a ray that's going parallel to the principal axis here. It goes to the center, and then it goes down like this, right? Well, that's not true. It doesn't really go to the center and then go down like this. It bends when it hits this boundary, and it bends when it hits this boundary. It bends in two places. But the net effect of it is if it went right to the center and then down this way. So it's easier to draw it that way because, in the end, that's what happens outside of the lens. What happens inside of the lens? Well, we had it really drawn properly. But it doesn't really matter for us because outside of the lens we had it drawn properly, if that makes sense. Okay. Same thing over here with diverging lenses. We draw it to the center, even though it's not really happening that way. It's bending differently than that, but the net effect of it outside the lens ends up being exactly the same. So we just continue to draw like that. Okay, what I'd like you to do is continue drawing the last four, please, where the object is at 2F, it's in between F and 2F, and then it's at F, and then it's inside of the focal length. Okay, see what you can do with those. I think just about everybody's finished drawing these ray diagrams. Now, what do we find about the characteristics in all 5 cases, no matter where the object is in this diverging lens? The characteristics are the same, right? The position, the exact position of it, the exact size of it will change, but the overall characteristics will be the same. It'll always be smaller. It'll always be upright, and it will always be virtual. So if you hold a diverging lens down against, like where you would a magnifying glass, and you move it back and forth, again, you're going to see a slightly different image, but it's always going to be smaller than the object is. It's always going to be right side up, and it's always going to be virtual, so you can never project it onto the screen. Make sense? Recognize this page? Looks real familiar. You know what? I like when I have to make up notes and I get to do this. I like that because it saves me some work. This page is literally just copied from a page, copied and pasted from a page that you've already done. When we did the mathematics of curved mirrors, we had two equations. Same two equations we have for curved lenses. Now we're going to call it the thin lens equation as opposed to the mirror equation. We also have the magnification equation, which looks exactly the same as it did for mirrors. The table, it's the exact same thing again. When are things positive? When are things negative? Well, the focal length is positive if it's a real focal point. Here's where you got to be careful, though. For a mirror, it was a real focal point when it was concave. For lenses, it's a real focal point when it's convex. Let's think of it in terms of converging and diverging. For mirrors, it was a real focal point when it was a converging mirror. It's a real focal point now when it's a converging lens. It just happens to be the opposite shape lens. So real focal point, and this would be for a converging lens. It's going to be negative when we have a virtual focal point, and that's when we have a diverging lens. What about DO? Well, technically when it's a real object, but that'll be always for us. Negative when you have a virtual object, which that's not going to happen for us. What about DI? Well, it's going to be positive if you have a real image. And it's going to be negative if you have a virtual image, and of course that can happen. What about HO? HO is positive if your object is upright. And it's negative if your object is inverted. HI is positive if your image is upright. This table is exactly the same as it was, isn't it? You just got to be really careful with that whole convex-concave thing. Again, it's converging. For mirrors, converging is concave. For lenses, converging is convex. The HI is negative if it's an inverted image. And finally, the magnification. Magnification is positive when the object and the image are on the same side of the principal axis. So in other words, if they're both upright, it's positive. If they're both inverted, it's negative. If one is upright and one's inverted, you tell me. M is going to be? Anybody tell me that? Anybody answer that question for me? It's a good question. If they're both on the same side of the principal axis, they're both upright, it's a positive M. If they're both inverted, it's a positive M. If one is inverted and one's upright, then it's a negative magnification, right? Just like it was for mirrors. All right, we'll do some examples with this tomorrow and some practice problems. They should go pretty quickly for you because, listen, we've done this stuff already, right? We've just done it in the context of mirrors instead of lenses. Have a good night, everyone.